start off there. So we just looked. We did a limit definition of derivative, and we took our original function x cubed, and we showed that the derivative function is 3x squared. And so what we shall start seeing, again, like we saw in the last one, we started off with a function that was a cubic, and using my limit definition of derivative, I got a derivative that was a quadratic. So once again, with this, we took a polynomial function, which was a cubic, and it dropped down a power. It went from the power of 3 to a power of 2 when I went from the function to the derivative. So we're starting to see a relationship between functions and derivatives. So the last one of these that we're going to be doing, we'll practice a lot with these. This is a trickier one, the trickiest of the three. We're now looking at y equals 1 over x, and that's a rational function. If you're familiar with it, it looks something like this. And so once again, we'll choose some point x and some point x plus h, and that is f of x, which equals 1 over x. And that point here is f of x plus h, which equals 1 over x plus h. And the instantaneous rate of change between them, if we draw a slope, and let this distance h get close to 0, the derivative, so the derivative, which is y prime, or dy dx, or f prime of x, or d dx of f of x. So all of these are simple, different ways of writing the derivative function. The derivative is going to equal the limit as h approaches 0, because once again, we want this distance here to get small so I can look at the instantaneous rate of change at x. So it's the limit as h approaches 0, and then we find the slope between these 2 points. So 1 over x plus h minus 1 over x divided by x plus h minus x. So we're starting to see that always, the x's in the bottom go away, and we're just left with h. So we're going to need to simplify the top, the numerator. And once again, we can't just plug 0 in for h, because we've got an h in the denominator, and if we put 0 in for h, we'd be dividing by 0, and that makes the whole world go really bonkers, and it's impossible. So we need to simplify this fraction so we get h out of the denominator. That's our motivation. So further going, we have the limit as h approaches 0. Well, we need to get a common denominator up here. And we're going to do that by multiplying this by x over x, and this by x plus h over x plus h. And when we do that, we get x over x times x plus h minus x plus h over x times x plus h all over h. It's getting a little bit confusing. It's a tough fractions, and we tend to not like fractions, but in this class, hopefully very quickly you're going to befriend fractions in a significant way. All right, so further going, limit as h approaches 0. Well, okay, looking at the numerator here, we have x minus x plus h. Being very careful to distribute this negative side, x minus x goes away, and we're left with minus h over x times x plus h, all divided by h. Well, this is an ugly fraction because we have a fraction embedded in a fraction, but it might be helpful to think of this bottom one as h over 1. So we have a fraction divided by a fraction, which we know we can write as multiplication. So it's the limit as h approaches 0 of negative h over x times x plus h. I'll write that a little clearer. Negative h over x times x plus h, and that's the numerator, that's this here, times the reciprocal of the bottom, 1 over h. And when we do that, these h's here can cross off. And I want those blues. Those aren't additional x's, those are the h's crossing off. So this, going further, is the limit as h approaches 0 of negative 1 over x times x plus h. And here, while we still have h in the denominator, it's not alone. And if we now let h be 0, we're letting h approach 0. If h now, the distance between those 2 points, became 0, we would no longer be dividing by 0. Because, let's see that. As we let h be 0, we've got negative 1 over x times x plus 0. This just simplifies to negative 1 over x squared. And we're not dividing by 0 here, so it's okay. So we just found that the derivative function equals negative 1 over x squared. And to keep consistency between this rule that I'm trying to have you develop and trying to have you to see, let's look at another page. What we just did is we took the function 1 over x, and we found out that the derivative function is negative 1 over x squared. And what I've been having you look at is how the powers of the function and its derivative are related. And I think it might be helpful to rewrite this as using negative exponents as x to the negative 1, and this is negative 1 times x to the negative 2, knowing that a negative exponent just turns it into a fraction. And once again, so this corroborates our findings so far, that going from a function to its derivative, the power drops by 1. So let's create a nice little table that looks at the 3 functions that we've looked at so far. So if I have the function and its derivative, I started off with x squared, and then had the derivative of 2x. And then I had, the next function we looked at was x cubed, and it became 3x squared. And the last one I looked at, writing it in terms of an exponent, we have x to the negative 1, and the derivative became negative 1 times x to the negative 2. And just to really hit this home, this is 2x to the 1 on that top function. It didn't have a 1, but if it doesn't have it, it's implied. So looking at the powers, the 2 went to a 1, the 3 went to a 2, the negative 1 went to a negative 2. And if you're really, really, really clever and trying to make some connections now, let's think about this. We've got a 2 here, and a 2 there, a 3 here, and a 3 there, a negative 1 here, and a negative 1 there. So I imagine for some of you students that want to jump ahead a little bit and make some big connections, without even using the limit definition of derivative, I bet you can figure out right away, if I had the function x to the 4th, what is its derivative going to be? Now, I'll leave that for you to tell me tomorrow morning when you show up to class. I'd like to hear from you right away. Even send me an email. If you're watching this video right now and you know that the derivative of x to the 4th, given this pattern that we're seeing, if you know what it is, send me an email and say, hey, Mr. P, I know that if f of x equals x to the 4th, then the derivative equals blank. But I'll leave that as an open kind of extra credit question for you.